Okay. So today we have Professor Saikat Ghosh. So Saikat will be talking about just the concept of measurement in physics in general, and how this is applicable in terms of the lab experiments that we do. So I am recording this meeting. This will be available on YouTube after the talk. So Saikat, over to you.
Okay, yeah. So this is a very supposed to be short. So I'll try to cover the concepts, like the basic concepts of errors in measurements, and also try to stress in this 50 minutes or so how important this is. Let me keep the time also here. So since this is a 5224, though I understand that both, I guess, third year and second year students are there. So just to kind of stress that this is one of the serious labs you're doing in terms of measurement. So just quickly, kind of like two quotes I have. These are like more slides for the MSc lab, but still the importance remains the same, which is basically, one is Lord Kelvin is kind of making the statement that I'll read it out, that I often say that when you measure what you are speaking about and express it in numbers, you know something about it. So, but when you cannot measure it, when you cannot express it in numbers, your knowledge is unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced it to the stage of science, whatever the matter may be. So he's basically saying, this is kind of one of the foundations of modern science, that, like whatever you're doing, you'll be reading optics, you'll be studying many phenomena, interference, diffraction, polarization, this, that. But finally, at the end of the day, you should be able to associate numbers with your theory, and you should be able to verify that. So that's kind of the spirit. And just because we are all in the pandemic time, like we don't really require sophisticated, extremely sophisticated instruments always to infer about the physical world. One example is Galileo. When he was a little boy, his parents used to take him to the Sunday church, and he would basically get bored there and watch the chandelier kind of going, oscillating in wind. And from there, and using his pulse as a clock, sorry, there's some background noise. I hope this doesn't start. Hello, can you hear me?
Yes, Saikat.
Yeah,
yes, sir.
okay. Yeah, so there might be this construction noise now on the back. So, let me start. Yeah, this is becoming a problem. The academic area, there's so much of construction going on. Yeah, so basically using his pulse, he discovered the fact that the amplitude of the pendulum is actually independent of the, like basically that time period is independent of the amplitude of the pendulum, for example. And that was a major discovery. In fact, that changed the way we think about clocks also, as well as simple harmonic oscillators. Can you hear me, Anand? Is the background sound too much?
No, I think it's okay. I mean, there is some sound, but
it's
manageable.
Yeah, I think I'm getting more perturbed by that. So, yeah, so what is the formulation to understand a general measurement? Let me write this. So almost always what you're doing in a measurement, let me get to the point. So you basically have a system, so this is your system. And let me call this with some variable X. This you actually couple to a measurement device, which actually gives you an output point. So this can be like, like for example, this might be, let me just give you very specific examples. For example, you might be actually measuring some voltage across a resistor, and this actually might be some current, you want to infer about. So you actually send it through your measurement device, which might be your, resistor across which you see the voltage drop. So in this particular case, this is a resistor, you're measuring across. And of course, this measurement also adds another very important thing. It actually adds what we would call noise or fluctuations. And this is another variable. So for example, if it's a resistor, then it gets heated up and current flows through it, so there are thermal fluctuations, and as a result, your final measurement result is basically your system variable plus the noise. And this is what you're basically, so what you do in any experiment, you measure y and infer about x. So y minus the fluctuations is x. So straightforward, and again, like since you will be doing PHY224, this x might actually, what you're trying to infer might be actually intensity of light. So imagine a laser falling on a photodetector. So it has some intensity, like your PHY103, you might have started already, that it's proportional to actually the electric fields square, and that actually falls, and it gives rise to a current in your detector, and this current ID, is actually proportional to the intensity of light. And you don't measure the current, as I was talking about the system and so on. You actually measure, for example, a voltage in a voltmeter, and from there, so you might be sending this current across a resistor and measure a voltage difference, and from there infer actually about the intensity of light that you're measuring. Right. So that's kind of a most general formulation of measurements. So it might get more and more complex. There might be feedback. The systems might be quantum. Those are finer issues. But the interesting thing about measurement is that both these things, like all these variables, the complexity comes in this inference because of the fact that all these variables, your x, your zeta, and y, these are all random variables. So I am guessing that all of you had exposure to random variables from your first year maths courses. So these are basically random, like, IID, identically distributed random variables, and with different distributions. So your resistor might have a certain variation. It might be fluctuating around a mean value. Maybe it's 10 ohms, but because of thermal currents, it might sometimes be 10.2, sometimes 9.8. Similarly, your voltage measurement. So you are using a voltmeter, and you see some reading, some digital reading, that might be fluctuating. And from this fluctuating numbers that you calculate, what we call data, what happened? So what we call data, from that data, that is a series of these random variables, you would like to infer things about the system X, and from this measurement of this random variable. So any questions up to this point? Please feel free to unmute your mic and ask any questions. Fine, everything makes sense. So, yeah.
So why can't we measure certain quantities directly? Like, for example, in this example, for intensity, we use the current generated by that light. So why can't we directly find some way to measure intensity?
Yeah, so so you will have to, these are again, like, you're asking deeper and deeper, these questions actually quickly get very, very philosophical also, what we can measure. But you can actually see that when we say, why do we not directly measure intensity? You will have to actually ask the question that what is intensity? Intensity is basically, kind of related to the energy of electromagnetic fields, and for example, what is a measurement? A measurement is something which actually gives you some numbers, 0, 1, 2, 3, and so on, some number line, you know. So basically here you're talking of something like an intensity, which is actually mod of electric field square, like C epsilon or something like that. So that is of electromagnetic field, and you're talking of measurement, which are finally numbers which should be displayed somewhere. Right? This is, by the way, like when you're saying that why can't we directly measure intensity, you are a human being who is asking this question, and when you say directly measure intensity, you still mean that intensity of electromagnetic field, which is a very hypothetical concept of like electric and magnetic fields, 103 towards the end, you have seen it's such a sophisticated thing that needs to somehow communicate with your intellect, right? Like somehow, like you as a human needs to read it as numbers.
Yes.
Right.
So it is basically my perception problem that I cannot perceive intensity directly.
Yeah, and basically, you know, like this actually gets very interesting, this theory of measurements, because finally, you know, as you're saying, this perception problem, in fact, you can say that all of this is actually just making our perceptions more and more sophisticated. Like, for example, like, you know, we see rainbows, we see all colors, but only when we actually do a very careful measurements, the kind Newton was doing with his own eyes, you start realizing that the eye is much more sensitive with the green light as opposed to red light, for example, you know, and that you need to somehow, that photons are falling on your retina, you know, and you are actually seeing this, these things, you know, this intensity. Somehow you need to actually translate that to a set of numbers. You might do that just by saying that, oh, this looks brighter in a scale of 1 to 10, I'll put a number, but you might also do it more systematically by coupling it to another set of devices where the electromagnetic excitation actually excites, for example, in this particular case, electrons. You know, electrons are actually energized by the electromagnetic field, and these electrons actually, when they pass through through resistors, you know, so they scatter off impurities, and that creates a voltage drop, which you actually can convert into numbers. You know, so you need to go from analog to digital electronics, which you read it as perception. Does that answer your question?
Yes, sir. Thank you.
Yeah. So basically, all I'm trying to say is that this is a very, very generalized formulation. And whenever you're saying that, why can't I measure this or that, you will see a lot of it is definitional. You need to pinpoint what do I really mean by measurement. And you will always see that it's like, you know, just always gets into more and more fancier things. So, okay, what happened? Why can't I flip? Is it hand? Okay, yeah, so I'll skip all these like different kinds of measurements, you know, I'll skip all that. Let me come to this basic point of somehow these things are, okay, the anodes are staying, let me remove this. Okay, yeah, so you know, like when we are measuring a value, so for example, you're trying to measure the wavelength of light in one of your experiments, it's actually, you know, like what in reality, what happens is there's always fluctuations, you know, so whatever you're measuring. So if I go back to that thing that, you know, if you see, you're trying to measure the intensity, you know, so the intensity of light, you know, if you actually see, so basically you have a source which is spitting out, you know, this light. It might be a laser, it might be a light bulb. You know, you actually put a detector here, you know, which gives you a photocurrent. I'm trying to stick to very close to what you will be doing, you know, and from here you actually maybe send it across a resistor, see the voltage. I'll come to that, but basically, you know, if you look at this current, for example, photocurrent, you will see that suppose I have an intensity I naught. I'm just taking this as an axis. So suppose I have an intensity I naught, you know, a particular point. Corresponding to that, you will find that actually the photocurrent is not quite a constant, but it will actually have a distribution. You know, so it will actually be distributed, and this is what I was trying to say when I said that, you know, there is noise of the measurement device. You know, so there is actually a distribution of this photocurrent. So for even if you somehow can pinpoint exactly a particular intensity which is coming from the source and falling on the detector, you'll still see, for example, if you're actually seeing it on a multimeter, which is basically a device where there are two wires you connect, and you will actually see a voltage or a current, you know, and you will see the current is fluctuating. You know, so if you actually, what I have plotted here is the value of current, you know, the photocurrent that you see. So let me call this I naught, you know, and this is some sort of a histogram, or, you know, the probability, or, you know, the occurrence. So you'll see that mostly you see the current around a particular value, but there is a particular distribution. It has a shape, it has a certain width, and it is not always constant for every time you look at it. Sometimes here, there, you know, it's kind of randomly distributed. And if you take enough and enough data, you will actually see this distribution. So this is like this kind of a fluctuation that you're seeing inherently from your detector is actually what is called an instrument error. You know, this is happening because your instrument is fundamentally has you know, fluctuations, but also you might actually just be lucky to have an instrument where actually the fluctuations are very small. It is an error, you know, which is smaller than your source. For example, your source is again a laser or a pointer, which is actually like, you know, falling on a detector, except that your hand is shaking. So, you know, this is actually falling back and forth. So basically, your source might have a distribution. You know, a source inherently might have a distribution because of the fact that, you know, it is a light bulb and not a laser, so not constant intensity. And even if it's constant intensity, it might actually be oscillating because of some process. Its distribution might be changing. And so you have another contribution, which is basically, you see, this is actually inherently statistical in nature. You know, you might actually, if you study this properly, and if your instrument's fluctuation is smaller than your source fluctuation, you might actually be able to say something about the nature of the source from which the light is coming, or the nature of the system, you know, what I drew earlier that you're measuring, you might be able to say something, right? So you're basically trying to pinpoint this I naught. And this is like throwing darts. So there are fluctuations, as we talked about, you know, inherently statistical fluctuations or your instrument fluctuations. And you're trying to, so it's like exactly like throwing a dart. So you want to hit the bullseye, the actual value of I naught, you know. But all your points actually might be like just off from that particular point. It might be equally scattered, or it might be actually systematically, you know, just away with very small little scatter. So you know, there are all different possible scenarios that might happen. This is actually the true value you're trying to find, you know. And these are all these things that you see here are just, you know, distributions depending on what kind of instrument and what kind of source you're using. So basically, you know, yeah, if you keep this analogy in mind of dart throwing, every data point is like, you know, like you're kind of trying to hit very close to that, but there are inherent fluctuations. You're making the angle, aiming, and so on. So then you can actually categorize. Let me see. Again, yeah, so maybe I have already talked about these things. So yeah, this random and systematic errors. So you can actually categorize these errors, and you can start asking the most important question, that what is the error in my measurement? So I'll skip all this, you know. So these are this random or statistical errors, you know, an error that varies between successive measurements, equally likely to be positive or negative, always present in an experiment, and appears obvious from distribution of values often. So basically, you will right away, like when you start measuring and quantifying, you will see that as you take more and more data, every data point is kind of different, you know, and so you have a stream of data, and the question you're asking is really, what do I do with this data? So any questions up to this point? I'm just going more into, how to think of these things and how to quantify them. So any questions, anything, so that I know that, the students are following. Okay, if not, let me just continue with that. So these are the dart analogy I was talking about. So for example, suppose you are looking at a particular set of measurements. So for some reason, suppose this is the true value. This orange one is the true value. What happened? Yeah, so the orange one is the true value, of the measurement, and the blue one is the data you have taken. So you see that the data actually has the right trend. It is parallel to the true value, what you expect theoretically, for example, or from earlier studies. You see that the errors are actually given by this. So we'll come to this. These are the standard deviation, of your data. So the errors are small, but it has a large deviation from actually the true value. So this is the analogy of dart, where basically the bullseye is here and you're kind of way far off. So this is what is called a systematic error, that every point systematically is away. So if you know the systematic error, you can calculate. For example, you might be using a voltmeter to measure your voltage, and you know that for every 10 millivolt you see, you actually, there is something, there is a 5 millivolt off. So if you know the systematic error, you actually can correct for that, and this is one error, or instrument error, which can actually be very nice to calculate. You might actually have systematics which actually are value dependent. In this case, you see this is the true value. The drift actually in the measured value, the blue ones actually gets larger and larger as X and Y gets larger. So in this case, you might actually need to, your systematic error is not a constant, but has a functional form. You might actually need to get that functional form and just subtract it out, But so these are all like different kinds of instrument errors, but you might actually have your data itself very noisy. You see, in this particular case, you're doing actually very close to the true value, but except that, your noise, your deviation in the error is actually very large, And in this case, really, you cannot do much. We'll come to this, that what you can do, but to actually state this error, which is actually the statistical error. And now we'll go into understanding what the statistical errors are and how to do better with this. So any questions up to this point? No. Let me ask then one question. Do you think that suppose I'm trying to measure an intensity exactly with this photodetector and I'm seeing it on a detector. Do you think if I take many data points, it will help me as opposed to taking few data points?
So it will reduce the random error.
Yeah, why should you reduce the random error?
Because we could,
or the statistical error.
So we would assume that the random error is equally random in both directions, in all directions really, and then we could just average.
Yeah. So suppose I take n data points. How will I do in terms of my random error? Do you have an idea?
Sorry,
I take 10 data points. Like, how will I improve? Like you are saying that my error, right? So suppose I state my error by standard deviation. So sigma. Everyone is familiar with sigma, the standard deviation?
Yes.
Yeah, so sigma, let me put this as standard deviation. So this is basically, so it's actually the average of the deviation from your mean, and your mean of your data after you have taken n data points is summation of xi. So you think so if I take like n like let's say like 10 data points as opposed to n equals 100, do you think the standard deviation improves?
Our estimation of the standard deviation would improve. However, the true values would stay the same. So we would eventually converge. So
I have written down the standard deviation. You cannot escape now. I'm saying this standard deviation, is that going to improve?
Yes, it is going to improve. It's going to converge to. It is going to converge to something, but it is going to improve.
Improve with respect to what?
Convergence to some fixed value.
Okay. So okay. Let me just get to. Anyone else thinks the other way?
Sir, I would like to
So we can have a better confidence interval for it, like for the same values. We maybe, if we reduce the deviation, we can be more certain about results that they would lie between these two specific values, which is our mean minus sigma and mean plus sigma.
No, like you're saying that what reduces?
So if our deviation, if we take more data points, we can be more certain about our results in the specific interval we are trying to.
Yeah. Okay. So I think like all of you are kind of hinting at that, but I want to make sure that like we are absolutely clear on this particular point. So so by the way, this is not a very trivial point, but you should think like these days, like it seems obvious that of course if you take more data points because you're asked to take in the lab like many data points, it must be good. But by the way, there was a big debate like during Euler's time whether actually more data helps. So Euler was a theoretician and he was actually strongly against this idea. He actually always thought that if you take a lot of data points, so you have some data which are bad data and some which are good data. So actually the bad data corrupts the good data. And he was like very, and Euler was such a, like probably the most powerful mathematician ever, and when he would argue, like no one could actually like really refute, except that there were statisticians, I'm forgetting their names, so they would actually kind of like say that, but practically we find that, as you take more data, what happens is like there are kind of repeating similar kinds of errors. So average number of times you hit the positive side of the value. You also roughly the same number of times you hit the negative side. So there's some sort of a cancellation going on. So that is one point I wanted to make. Yeah.
One more thing is that, so like what if your measurements are at the point where you cannot say you're at the minimum threshold where the error in your measurements is as less as it can be. So when you take more number of measurements, okay, suppose for an example, I'm trying to measure a value which is at 1 and my error is always plus or minus 0.1. Then my standard deviation won't change, but I will just be more confident about my standard deviation.
Yeah.
So when you take more number of measurements, it's not going to improve. It may or may not improve, right? It depends upon your measurements.
Yeah, so actually like that is why I'm saying that let's just go slowly. These are actually all very important point. In fact, just one of you, before I forgot to see the name, mentioned that, your estimate of your error improves, which is kind of closest to the right point. In fact, the point you just now mentioned is also correct, that, like suppose I am using a scale to measure a length of a stick and the end of the stick falls at a particular point, and I put every time and it's exactly matching with 10 centimeter mark, so like how come repeated measurement is going to help, so where it helps, where it doesn't help, let me come to that again.
Sir, could we say that the deviation in deviation decreases as we increase the number?
No, yeah, that is also true. That's also like, let me come to this. Like, in fact, let me just use this point to kind of define, since we had a nice discussion. So, what is it that we are actually trying to do? So, let me first set up the problem, right? Like, so you're taking data, right? So you are just consider a set of data. Just one second. So consider a set of data xi, you know, so this is like x1, x2, xn. You know, you have collected, and you have collected from the, okay, I think I've changed, sorry, it's kind of getting mess. So this was just accuracy and precision. I think I have already talked about this. Let me just find a white area so that I can, or maybe let me just, yeah, maybe let me, this is a good spot. Let me use this area. This is kind of an empty area. I can use this too, right? So yeah, so basically you see that the problem we are asking is that we have a set of data. So xi is my set of data. So this is basically x1, xn. And so I am actually choosing it from a system X, right? So it has a, so x1, x2, xn are all random variables chosen from a particular distribution, you know. So let's say that the distribution has a is Gaussian, you know. So so basically, let's say that the original what people would say, you might be familiar with that, the probability distribution function, you know, let that be Gaussian. You know, so it's actually being taken from Gaussian distribution sigma square minus x minus mu over, just check the normalization off. You know, so this is the probability distribution, you know, px, pdf, from which it's being chosen. So you are asking the question that, you know, what is the mean, you know, like, so what is the, so you see that this is your original system. So this Gaussian distribution is what describes your system, and you want to estimate, you know, the mean, and you want to estimate the standard deviation sigma. I am taking a specific problem where you are actually drawing your data from a system which has where this variable x has a Gaussian distribution. You can imagine Gaussian distribution is actually a very common distribution to take, you know, and your aim really, you know, why you are doing this measurement, your aim is to estimate this using this random variables. You want to estimate mu and sigma. Is the pretext of the problem clear? If you see, like, this is like we are actually, since there was this whole discussion, I'm going into this. So this is really the most general formulation of a measurement, that you are actually trying to measure intensity. You make some assumption about the intensity of the light, that, you know, it's distributed, it has a probability distribution. So every time I see this fluctuation, it's statistical, and it's being drawn from a probability distribution. When I say that I know the average intensity, I basically know this probability. If the probability distribution, for example, is Gaussian, it's distributed like that, about the center mu, this I'll call as my measurement of the average intensity. And then I can ask that, for example, what would be the standard, like what would be the deviation of my estimate of them, right? And similarly, I would like to have an estimate of the original parent standard deviation, and what would be the estimate of that, you know. So this is really the key question, you know. This is really the point, and it turns out that the estimate of the mean, what I was writing before, estimate of the mean, you know, x bar is actually 1 over n xi. So this is, I'll just, unfortunately the course is like, this is just a one-day course. I don't know whether I'm already running short in time. So let me just state this, that you can actually show that x average, if you take over many sample spaces, this actually becomes like 1 over n summation over xi. So this is actually just n times mu divided by n. So this actually gives you the right estimate. You can now ask, what is the, this is a long story, I'm drawing it short. What is the error in this estimate? You see that x bar is my mean. What is the standard deviation of the mean? So this is the standard deviation of the mean. You see, this is not the standard deviation of the data. This is the standard deviation of the mean, standard deviation of my estimate. This actually turns out, I don't know whether I'll have another place to write. I'm sorry for this whole mess. So this standard deviation of the mean, sigma x bar square, let me write down. So this is, again, I'm writing down this. This is standard deviation of the mean of the estimate. And that actually, if you do the maths, it's very nice to do it. It actually goes as sigma square over n. So originally, your every sample was being drawn from a distribution which had a width sigma, and every data point x1, x2, xn. So you see that now you have collected this data point, and you have collected, you have calculated a mean, and you are asking what is the standard deviation of this mean. That is actually the standard deviation square of the individual measurements divided by n, which is based, or rather this is n. So it's actually telling you that if you actually, take many data points, every data point has fluctuation, but that way, in the estimate of your mean, you actually make your error smaller. That's all that you do. But you see that now, if we actually take the example of, for example, a ruler, you're using, and you exactly fall here, and it's told that the ruler has a, it's exactly falls at 10 centimeter, and you have 0.1 and 0.1 marking. Here, no matter 100 measurements, your point will exactly fall at that point, and there's nothing excess to do. So there, basically, you see there's absolutely no standard deviation of your mean. That is exactly 1 point, except that every point, it has now this sigma, which is basically your instrument error. Any question up to this point? This is actually a very deep point. I just kind of since there was a discussion on this. Any question quickly?
Sir, what is standard deviation of mean?
The standard deviation of mean is basically what you're calculating. So, sorry. It is, if you can see this corner, so this is x bar minus mu, so let me just write it this way. So this is x bar minus mu whole square average. So this is, you see, I have this is very important to understand that this x bar, the mean, actually itself is a random variable. Actually, if you see, each of these are being drawn from a random variable, and each x bar is constructed. If you repeat this experiment of drawing n samples, like let's say m number of times, then x bar actually becomes a random variable, right? And this x bar now actually has a set of distribution, and you see this, because now this x bar is a random variable, the key question you're asking is that I know what is this x bar, which is a random variable. The mean itself is a random variable. And what is this random variable? It is actually constructed of a series of random variables, sum of series of random variables, which are all drawn from a distribution which has a mean mu and a standard deviation sigma. So this is a new distribution. X bar is a new distribution. It's a very important question to answer, how this distribution looks like. it turns out it's a very hard question to answer. But what you do answer is that, the distribute, like what is the mean of the distribution? So that is this X bar average, here I'm drawing, and that you can actually show that mean of this collective distribution of n data points, each of them taken from a random distribution. Very surprisingly, that mean actually turns out to be the sample mean or individual population mean, but the standard deviation of that random variable is actually standard deviation of each of them divided by n. So does it answer your question?
Sir, this xi mean is actually means xi.
You're taking n sub another random variable, which is x bar.
Sir, in bottom right corner, you wrote x bar mean equals to
Bottom
1 by
right.
n sum.
Yeah, 1
Yeah,
by
yeah.
n, see x bar. So this is the relation, no? This is your estimator. So x bar is 1 over n summation xi. And now this is the average x bar. So this is 1 over n average xi. Average xi you can calculate because you know this thing. So you can calculate the average xi. That is mu, n times mu. So this is mu. So average of x bar is mu. What is x bar squared minus x average square? That's the thing, and that is what is this sigma x sigma squared.
Okay.
Does it make sense? Any
This
other question? Yeah.
Sir, when you're taking the average of x bar, so what you're doing is that you're taking n data points and are you repeating the experiment multiple times?
Yeah. So you're basically, you see that, so this is like normally what you do, right? You are actually taking this n data points and you construct an x bar, right? So, and normally you state that, but you see this x bar is just one realization. If you would have taken this n data points and constructing xi, you see that each of these xi is a random number. So in principle, x bar is a random number. Right? And what is your aim? Like, why are you even constructing? It turns out that the reason I have written x bar as 1 over n summation xi, there's a whole thing behind that, the theory of maximum likelihood. I don't want to even go into that. But, why are you even constructing it like this? Because of the fact that if you construct a random variable like this, and for example, if you actually repeat this, such group blocks several times, you take an average, you will actually converge better and better to your actual value. So,
yes.
So for example,
every set of experiments we take, we essentially get a 1 over n factor there.
Yeah. It in fact turns out like exactly, like we have been only talking about estimating the parameter mu, which is the average, maybe the average intensity. I have not even talked about estimating sigma. I think earlier the first comment was on that you can also ask like, how can I estimate sigma? Like these are things to ponder about. Unfortunately, I'm kind of running at the end of the course. So we just talked end of the class. We just talked about, how do you estimate the mean and what is the standard deviation in the estimation of the mean, standard deviation of the mean. Similarly, you can ask how should I combine my data points to actually get an estimate of this error sigma, And it's very interesting. It's actually like turns out that the estimate is 1 over n minus 1 times summation xi minus x bar square. But I'll skip all that because there's a very important point. Any other question quickly?
Just one last question.
Yeah.
What exactly is the advantage of doing m experiments with n observations instead of just doing one experiment with mn observations? You'll get the same results output wise.
One experiment with what do you mean by that?
We are taking n observations, finding x bar, then creating multiple x bars for every n observations, and then finding the mean of those x bars.
Yeah.
So instead, if we did one experiment where we take m into n number of observations, would we get a similar result?
Yeah, I think so. Yeah, I think so. I don't understand exactly what you're saying, but I think what you're trying to say is that, yeah, you can combine all of them and you'll get a very similar n of them, like n of them, and you get you take n data points, you get one number, but now you would like to see this sigma square over n, right? So you know that the distribution of x bar, like you get one number and you know that the distribution of that will be sigma square over n if you go through the this theory of maximum likelihood, except that to see the distribution you will have to take now m such x bars. Then you can actually calculate the average of x bar, and then you can calculate the standard deviation of x bar, and if everything is fine, that standard deviation will be sigma square over n. You see, and totally you have taken n times m. So you can actually do the whole analysis together and you will get sigma square over n times m. Do it properly.
Okay.
Yeah.
Sir, I have one question.
Yeah.
So this entire discussion was this discussion started with assuming the fact that the underlying data comes from a distribution with the Gaussian PDF. But in reality, it is usually this PDF that we want to find. So we can't assume something like this and then work with it, right?
No, actually, Anand, how long do I have?
You have about 5 minutes. I mean, it's up to you. I mean, the class is over at 3:50, but then it's up to you.
But I have another class where I'll be talking about exactly the same thing.
Okay.
So I think this was a very important question. What was the question? Can you repeat that again?
Sir, so I was asking, is that our data is originally coming from a distribution which we assume to be Gaussian, but it is this distribution that we want to find.
Yeah, exactly. So couple of comments on that. Firstly, if you see, like, let me just come to the main thing that I couldn't come. Maybe Anand, we can have another discussion one more day. Maybe a half a day discussion. But basically, really the question is that I like often in measurements you measure x, measure y, and then combine to create a new quantity z, which might be like z is equal to xy or z is x divided by y. And if you know the distribution of x and distribution of y, you would like to know what is the distribution of z. If you know, like what kind of variations, these are all random variables. What are the variables in x and y? You might actually ask the question, what is the distribution in z? But so these are usually very, very hard questions. And these are actually questions of estimation and questions of inference. In fact, even if I tell you that this is Gaussian and this is Gaussian, actually to show that this z is Gaussian, particularly x divided by y, it gets skewed Gaussian. It's not a Gaussian. But there's something very interesting. It's called the central limit theorem. It basically is something very interesting. It says that when you have a large sample space, when you start taking more and more and more samples, so exactly the same question I was coming to, this x1, x2, xn, each of these are random variables, and you might combine them to create this mean and standard deviations, which are also random variables. As you start taking larger and larger and larger n, and you see each of them are coming from different probability distributions, and as the question was that, these are all like P1, P2, like they might not be Gaussian. There might be some other distributions of crazy kind, as long as, let me just state this, there is no time to prove this. So the statement is the following, that as long as this original PDF of xi, original PDF of xi has a first and second moment, so has as long as xi and xi square exists, so as long as first and second moment exists, it turns out that if you take many such identical distributions and combine them to create a larger distribution, you know, like which is this X bar or something. So this, in the limit of large n, as n tends to infinity, actually effectively is described by mean and the standard deviation. So, and basically the interesting thing about Gaussian is that that's the only distribution in continuous variables which actually just has two moments, the mean and the standard deviation, you know, so just two moments. So this is a very, very powerful theorem. It's actually like the you know, comes back over and over again in physics. It turns out that that sigma square over n we very briefly talked about. Today was just kind of roughly talking about the issues. I have not even talked about error propagation, but basically, you know, it turns out that like all distributions, as you take the numbers very large, they start behaving very Gaussian. So
yes, so that makes sense.
Yeah, does that? Yeah. So actually, like I think I deviated quite a bit. So like we didn't do this error propagation. So this is also very interesting that, you know, like roughly for many almost all continuous variables, you know, in this very large data size, they behave Gaussian. So if X and Y are Gaussian, you know, so if Z is a function of X and Y, then it turns out that you can actually, under certain conditions, you can actually write down the error in Z, estimation of Z, you know, as in terms of the errors in X, you know, del F del X squared plus sigma Y squared del F del Y squared, you know, under certain conditions, very restrictive but extremely widely applicable conditions, you can write this kind of a formula, which is actually the most important thing I should have talked about, but we couldn't get a chance to do that. Maybe in another half an hour class, we can discuss the issues and like any doubts and so on. Any questions up to this point? Does that answer that question? That why, like, you know, like there's nothing about Gaussian. That earlier Gaussian statement, I just took Gaussian as an example. You could have done it with something else. But it turns out this central limit theorem is very real, that arbitrarily different probability distribution, as long as the distributions are such that average of X and average of X square exist. By the way, like that is not necessarily true for all probability distribution. Anyone can give an example of a probability distribution for which the mean and the standard deviation doesn't exist? Anyone knows the probability distribution for which
Cauchy distribution?
Yeah, Cauchy. Yeah, Cauchy. Yeah, great. Or what we also in optics, you will see this course also a lot with what we call Lorentzian distribution. You cannot calculate the mean or any of the moments because there's a cusp at the zero. So for this, the central limit theorem will not work, but otherwise. Okay, so Anand.
Yes.
So
yeah. So, well, if there are no further questions, again, you don't have much time. So I think we can do a half an hour session some other time.
Yeah, some other time. Yeah, just kind of like.
Is this Thursday okay?
But I think, yeah, this Thursday again I have a like I think that the same problem.
Next Tuesday.
But next Tuesday will be great.
Yeah. Fine. So we'll find half an hour for you then. Okay. Okay, so let's thank Saikat for the fantastic talk, and I'll put this talk on YouTube so that everybody can have access to it. Okay, thank you so much, Saikat. Thank you.
Great. See you.
Yes, sir.